Okay, so I can start?
Yeah, please go ahead.
So first of all, I'd like to thank a lot Irene and Miguel for the very nice invitation to be back to Harvard to give a seminar. I was there already last year, so it was a very pleasant, very nice visit. So the talk we are going to give today with Carlo is based on a paper with Quentin Bonfoy, who was my former student, is now in DESY, Hamburg, and Cezar Condeescu, another former student who is in Bucharest. It's based on this paper, and it's called String Defects, Supersymmetry in the Swampland. Yes. So that's the outline. So first of all, I'd like to review the main idea. The main idea is to use the anomaly inflow on string defects to constrain higher dimensional theories. And today the subject will be exclusively on 6-dimensional theories. Then I'll present, before discussing explicit examples, a conjecture in which we try to conjecture a new consistency condition based on what we know about the perturbative strings. And then I'll present one example. So let me just tell you that we splitted the material with Carlo such that I'll talk only about supersymmetric examples, and Carlo will talk about examples with broken supersymmetry. You'll see more precisely what kind of supersymmetry breaking you discuss. Okay, so let me start. So with the couple of general things. So first of all, the idea of the Swampland was proposed by Qumran some time ago. The idea is to try to constrain quantum field theories by coupling them to quantum gravity. Idea being that not all of them can be coupled to them, and the ones which cannot constitute the Swampland. There is a nice review by Eran Palti that probably all of you know. Now, there are various, as you know very well, there are a lot of conjectures, mainly due to Qumran collaborators, but today I'll concentrate to one of them, to one approach, which personally I find nice in the sense that it allows, it's a way to test if a field theory is consistent by by coupling it to string defects, by considering string defects in this theory. So the question is if there is a way to test that the field theory which satisfies all anomaly conditions in a generalized sense, or Green-Schwarz, can be consistently coupled to gravity. And again, we had this nice recent approach by Qumran collaborators. By the way, the main paper which will be relevant for us is the first one. So this was initiated by Qumran, Kim, and Xu last year. There was a couple of follow-up, including by people in the audience. And our idea was to use the perturbative data, more precisely perturbative type 1 string data, to test these conjectures, the consistency, to test the consistency conditions they proposed, and to enlarge eventually the set of consistency conditions with supersymmetry, and that's what I'll talk about, or broken supersymmetry, and that's what Carlo will talk about. And again, I think the final goal of Swampland program, at least from my perspective, would be very nice to really constrain the usual beyond the standard model cosmological construction. That's my personal goal, my personal motivation to work on this subject. So let me start with a review, first of all, of what is known in 6 dimensions. Again, I exclusively talk about 6 dimensions today with 1-0 supersymmetry. So first of all, the anomaly cancellation conditions 6 dimensions are, as you know, are very strong because we have gauge gravitational anomalies. First of all, in 6 dimensions, we have the gravitational multiplet, we have hypermultiplets, vector multiplets, and tensor multiplets. And in order for the reducible gravitational anomaly to cancel, we have this relation between the number of hypers, vectors, and tensors that is well known for so long time. The interesting part in 6 dimensions is that there are various, there is a generalized Green-Schwarz mechanism in the sense that there are various two forms, tensors, which can participate to the Green-Schwarz mechanism. This was emphasized by Augusto Sagnotti. And the anomaly polynomial, if we concentrate only on the gravitational part and the non-abelian factors, this will be the ones which will be relevant for us. So we neglect abelian gauge factors today. Then this anomaly polynomial factorizes in this way, where omega is a metric which has a signature 1, nt, with nt is the number of tensor multiplets. And x4 is this 4-form polynomial containing the gravitational part. And this is the gauge part for the various gauge group factors. The anomaly, you see, dimension can be cancelled by adding some couplings of the two forms. These are the tensor two forms to this 4-form appearing here. So this is naturally a 6-form in 6 dimensions. And the anomalies generated by the spectrum of the theory is cancelled by having by these couplings. So the field strength, as usual, in the usual Green-Schwarz mechanism, contains a contribution. So the field strength of the tensors contains the contribution from the Young-Mills and the Lorentz part, such that the two forms are not invariant and they transform a certain way under the gauge and gravitational transformations. And what will be very important for us today is that this theory can have, since there are tensors, they can couple to string defects. And the string defects are therefore, the couplings are defined by a certain charge vector. The number of components is the number of tensor plus 1. The one is the one from the gravity multiplet. And the couplings are these ones here. So so this is the coupling of the tensors to the string defects. And as usual, what will be important for us is the so-called anomaly inflow. So even if the anomaly in 6 dimensions is completely cancelled by this generalized Green-Schwarz mechanism, there will be inflow of anomaly on this 2-dimensional defect. And this is the inflow to generate it, written in this anomaly polynomial form, where what you see here in addition is that this is the Euler class of the normal bundle from the 6-dimensional point of view, perpendicular to the string defect. And this anomaly has to be cancelled by the degrees of freedom living on the defect, which is a 2-dimensional conformal field theory. Now, so we defined in this anomaly polynomial, we had these vectors, one coming from the coupling to this gravitational part, and the ones coupling to the gauge group in 6 dimensions, A and B, which will play a very important role in what follows. The products, their scalar products, by the way, here the scalar product is defined with this omega tensor here. So this would be Q times C2. So all the products are defined with this object here, metric, which is this 1, nt signature. All these products which appear in the 8-dimensional anomaly polynomial are actually integers, all these scalar products. So this defines an integral lattice, and the reason for this was described in various papers, in particular this paper by Deser et al. It's related to Dirac quantization conditions for a die on the 6 dimensions, can be seen also from a field theory perspective. In addition to these, there are arguments, this will be important for us, there are arguments that the corresponding lattice, which is typically called the anomaly lattice, has to be self-dual by Seiweg and Washington Taylor. This implies that there is a basis in which these vectors A and B have integer entries. So these are vectors, and there should be a basis. By a basis, I mean a basis to write the anomaly polynomial. I'll come back to this, in which these vectors have integer entries. Now, what I mean by basis is the following thing. The anomaly polynomial, it's a quadratic form in nt plus 1 variables when nt is the number of tensors. Sorry, it's nt plus 1 times the quadratic form, but depending on an ng plus 1 variables where ng is the number of non-abelian gauge group factors. Now, if you have a large number of tensors compared to the number of non-abelian factors, the factorization of the anomaly polynomial is not unique. And therefore, we can write the anomaly polynomial in various ways. Some of this non-uniqueness is related to this SO1, NT transformations. And for us, we'll have two bases of interest. The most important for what I'm going to say in a moment will be this integral basis. I'll call it integral basis, in which A and B have integer entries. So this will be the name I'll give it, integral basis. And there will be another basis, which will be the one which is really singled out by the string theory, which Carlo will introduce it, I think, in more detail, which is the geometry where which d-branes an orientifor plane C from the point of view of their couplings to this tensor in 6 dimensions.
Is the geometric basis a sub-case of integral basis?
No, actually, as you'll see, the geometric basis, in the geometric basis, usually these vectors do not have integer entries, but that's the basis which the string theory prefers. That's the basis in which from the string amplitudes, you can immediately see the geometry of the branes on orientifor planes. I'll give you an example of this geometric basis, and Carlo will give you another example. But it is true that we're always been able to identify then this integral basis, which is used, for example, in your paper. This basis still always exists, but this basis, usually integral basis, it's a kind of, the tensor in this integral basis are a linear combination of the string tensor, actually. So this geometrical basis is the one in which the tensors are really the ones appearing in string perturbation theory, where in the integral basis, you have linear combination of these tensors. Okay. So again, Carlo will say more about the geometric basis. And I also say a little bit, but not much. Now, let me review now the consistency condition which are worked out by, in this paper by Kumron with Kim and Xu last year. First of all, in supersymmetric model in 6 dimensions, the consistency moduli space of scalars in tensor multiplets require for the existence of a vector which I will call Keller form in what follows, which satisfies this kind of relations. The scalar product with itself should be positive. The scalar products with this B's appearing the gauge part should be positive. And one more condition, which is, I think, less understood, is related to Gauss-Bonnet term, but as far as I understand, it's we'll impose it anyway and doesn't seem to change much the picture. With these notations, Kumron and collaborators worked out that the left and right central charges on the 2-dimensional string defects as a function of these vectors A and this charge vector of the corresponding string. So these are the formulae. And by imposing this C left, C right to be positive, and also a couple of more conditions that they describe in details there, essentially the levels to be positive and the levels of some SU2.
Emilian, sorry, can I quickly interrupt to ask something? So there you say that the levels have to be bigger or equal to 0. The equal 0 case, is that marginally okay? Because you would imagine that the current worksheet is not unitary.
Yes, yes. Some of them can be 0. Yeah, yes. And I'll give an example in what follows. Yes.
Okay. Thanks.
Yeah.
This is a BPS string.
Yes.
Yeah.
For me, I'm only talking about superstring. Sorry, only about supersymmetric case. And I'll just make one comment about non-BPS string defects, but this is for the BPS ones. And actually, I'll make some comments about C left, C right. C left, C right would have additional contributions, actually, even for BPS ones. And this is also explained in the paper of Kumron, and we have a more microscopic touch on it. But yeah, for
Sure,
timing, I'm talking about the BPS. So the conditions they wrote are these ones here. This is related to the fact that the tension of the defects will be positive. This is related to all this C left, C right, and some levels to be positive. And there is an important condition to the theory to be unitary in the sense that the contribution of the Kac-Moody algebra to the central charge C left should not overshoot, should not be bigger than the real central charge, which is given by this expression, or actually can have an additional piece here. It can be slightly bigger. C left, which actually is always bigger than what is written here, strictly speaking, bigger or equal. Now, the object which we are considering here, so our setup is 6 dimensions, type 1 string. I don't think we miss much if we consider T-dual or antifolds like type 2B to 2A. I think everything is contained here. So we consider type 1 strings, and the objects which will appear in our construction are the following. First of all, there are the background branes, and we are considering actually to be more explicit orbifolds in 6 dimensions. So these objects, first of all, the type 1 string has D9 branes, the 10-dimensional Young-Mills sector. In orbifolds, there are typically also D5 branes, which are localized in the internal space. So here we have the 6 dimensions, and we'll have a 4-dimensional space, which in which we'll do typically, which is typically orbifolded. So these are the background branes. The number of these background branes are fixed by Ramo-Ramo-Tadpole conditions. And then we have these string defects we are considering. The simplest one is the D1 brane, which is localized everywhere except in these 2 dimensions here. And then we can have D branes wrapping the internal space, which are also strings from the point of view of the 6-dimensional theory. Now, these D5 branes, which we call D5 prime, have also the properties that we can add the various internal magnetic fields. So here you can have a very large class of, if you want, string defects from a 6-dimensional point of view, because you can have background magnetic fields here. Okay, so that's what I said here. We can also add self-dual magnetic fields configuration on D9 branes. Also generates various models, which are, by the way, T-duals to intersecting brane models. The number of these objects are, again, constrained by Tadpole conditions, but the magnetization on these D5 primes are completely arbitrary. These objects, these string defects, are not constrained by any Tadpole conditions, so you can have arbitrary kind of configurations. And the ones which are stable are of 2 types: self-dual configurations. You can put self-dual configurations. You can see them if you want as an instanton configuration in the internal space if you want here. This would be BPS ones, preserving the same supersymmetry as the orbifold. You can also have, in the example we discussed, anti-self-dual configurations, which are non-supersymmetric, but they are stable. So these are examples which discussed on our paper, in which we have stable strings defects, but not supersymmetric. Overall, we have a pretty big landscape, if you want, of models and string defects in which we can test these consistency conditions that I wrote before. So this is what we did. And let me give you now let me talk first of all about this conjecture, first of all. So the conjecture is the following. So in all the examples we checked, in which the 6-dimensional theory had at least one tensor multiplet, and we checked all what we could with models which have a known string or F-theory embedding, we always found string defects which has this null current of charges. Now, let me give you, we don't have a full proof. So we don't have a full proof that any 6-dimensional quantum field theory coupled to quantum gravity should satisfy. We have only arguments coming from string theory. So that's why we call it a conjecture. Now, the string arguments are the following. First of all, in orbifold examples, these are typically bulk strings, string defects which are off fixed points, which move freely in internal space. And the reason is they have this null charge is because they couple to the untwisted tensor in the, so there is always an untwisted tensor in 10 dimensions which descend in 6 dimensions to a self-dual, anti-self-dual part. And these strings coupled with equal couplings, these bulk strings, if you want, coupled with equal couplings to these objects, and automatically lead to these null charge strings. So in geometric constructions, we believe that this string should always exist. We believe. More generally, if you remember the anomaly polynomial I wrote here, actually these null charge strings are the ones whose anomaly polynomial is independent on the normal bundle, actually, more generally speaking. So if you have an anomaly polynomial which is independent on the normal bundle, automatically you get these null charge strings. We didn't find any counterexample, but as I said, we don't have a full proof. So we conjecture that such things should exist in all consistent field theories, and we use it to test, to exclude some examples which have no current string and F-theory embedded.
So the completeness of the spectrum does not guarantee this, does it?
I'm not sure. No, I don't think so. I don't think so.
You know, the nodes combined with the integrality and the completeness, this doesn't give you this?
We didn't find an argument. If you have an idea offline, I might be happy to, but we don't have other argument than this one's here. I'm not sure the completeness implies this. I'm not sure.
I think one can write down self-dual lattices that don't have vectors aligned in such a way that they have zero norm. So
from a field theory, certainly. And again, these are very specific kind of strings. I mean, but in absolutely all examples we checked, I mean, we took all the orientable literature, we took all the F-theory literature we could find, and we always found these objects. But I don't think there is we are not aware of a full field theory, pure field theory argument, personally.
Can I ask? So there's one conjecture constraint for the 6D vector, you know, for the anomaly vectors that, as far as I know, has no proof, which is that the gravitational anomaly vector A has to be a characteristic vector of the lattice. So its inner products with any vector in the charge lattice have to be, you know, they have to have the same parity. So Q times A must have the same parity as Q squared for any Q. Is there any way that anything like this could be used to argue that even though this is not true in a general lattice, it might be? I'm asking, have you thought if properties like this?
I'm not sure this is true. I mean, I think I know counter. Is
Oh.
it obvious?
No, I'm.
Just a second. I'm not completely sure if this is. Just a second. Well, no, actually, no, I don't remember anymore. But you are saying QQ and QA always have the same sign?
I'm saying that that the vector A is a vector in the lattice such that for any Q dot Q has the same parity as Q dot A. And then maybe you start with any Q and then you start shifting by A or something. And I was just trying to think like properties that we know about the charge lattice that could be related to saying that Q dot, that it has to be a Q squared, which is 0.
Okay. Again, as I said, for the time being, I don't have any more argument, but I'm very happy offline if you have.
No, I was just asking if. Yeah.
Yes. No, we don't know. We don't have a full proof.
Thank you.
I think.
If you don't mind, actually, one more question about this condition. As you said, these examples you find are typically moving freely in the internal space, and so obviously you're not just looking at examples that strictly descend from 10D. But if you do assume that your theory descends from 10D, is this automatic?
Yes. So
yes. Okay.
Yes, but we also looked at other examples in the literature, and we didn't find counterexamples. But we didn't spend months searching, so maybe we don't have a full search. I don't know. Right,
but you're saying that this string at least behaves like it was coming from 10D. Yeah.
Yes.
Right.
For this, I think we checked everything we could. Yeah. So let me give you 2 examples. One is this one. It's given by Kumar, Morrison, and Taylor in 2010. So it's an example in 6 dimensions with the gauge group SUN, one tensor, a hyper in symmetric representation of the gauge group, and n-8 fundamental representations. And this defines the integral basis in which all these vectors have integer entries here. That's this omega metric. And the null charge strings should be of this type, or epsilon plus or minus 1, okay? Because it's just one tensor, so it's a two-dimensional vector. And now it's easy to check that this charge vector violate actually, if you put together all of these constraints, it cannot satisfy simultaneously all the constraints. I'm not getting into details, but you can find the argument in our paper. This charge vector does not satisfy all of the constraints of Qumran collaborators for any n, by the way, for any n. So seems to us that these kind of models are excluded for any n according to this argument. And previous results were n smaller than 30, I think, in the original paper, and then Qumran collaborators put these bounds for the constraints they found. Let me give you a second example. It's based on this gauge group, it's 24 times SO8. Sorry, I cannot see. I cannot see. Let me move a little bit. Okay. One tensor again, and 3 antisymmetric hypers from the antisymmetrics. I forgot. Probably SO24. I forgot antisymmetric with respect to whom. Okay, and the integral basis. These are the vectors, the anomaly, these vectors A, B1, B2, and again null charge strings, which are of the same form as what I showed you before, of this form here, cannot satisfy all these constraints here. So these are two examples we found that you can exclude. Okay, so in the last no, I think I finished my time. I think maybe I should just, yeah, I finished my time. Maybe I should just tell you that in the supersymmetric case, so we analyze the supersymmetric, maybe let me go just for 5 more minutes if you allow me to do this. So we studied, for example, this 6-dimensional orbifold. This is the simplest 6-dimensional supersymmetric orbifold in 6 dimensions, which was worked out by Bianchi Sagnotti and by Gimon Polchinski later on. So this is a model which contains D9, this is a Z2 orbifold. It says 1,0 supersymmetry in 6 dimensions, has D9, D5 branes, and OF9 and OF5 of the regular orientifold types, which means plane types, which means negative charge, negative tension, both of this O9 and O5. And this is a model which contains one tensor from the untwisted sector, 4 hypermultiplets from the untwisted sector. I'm talking about the gravity sector for the time being. And there are 16 twisted sectors, each of them hosting 1 hypermultiplet from the gravitational sector. And then there is a gauge sector, open string sector, which is a U16 times U16 gauge group, and some hypers in the antisymmetric representation and bifundamentals. So the details are not very important, but that's arguably the simplest 6-dimensional supersymmetric type 1 model. So in such model, in this model, let me just tell you that in this model, the string theory prefers this factorization of the anomaly polynomial. So in this sense, in which sense is the geometrical form I said before? Remember, this model has 1 tensor multiplet, and it has 1 tensor in the gravity part and 1 untwisted tensor, if you want. And if you like the string amplitudes, that's what you see. You see that the one in the gravitational tensor couples to the gravity part and to 2 gauge factor with the same coupling to the same strengths, and then the other tensor coupled with opposite coupling. That's what you see from the string amplitudes, and that's why we call this the geometrical form of the anomaly polynomial. Now, in this form, in this factorization, these vectors are not of integer entries, as you see, so it's not an integral basis. However, if you compute this scalar products, they are integer. So the lattice is manifestly integral, as you see it here. It's not manifestly self-dual in this geometrical basis, but you can go to the other basis. And the other basis is written using this omega metric and using this factorization of the anomaly polynomial, which is pretty well known also. And then you see that that's the integral basis indeed. Now, let me give you the one example. So the kind of string defects you can imagine here, there are again various types. We have this mini landscape. I'll only discuss about these D1 branes, the simplest kind. D1 branes can be at the origin or the orbifold fixed points, or can be at different fixed points. The origin is peculiar because it hosts also the 5 branes here. So if you put these D1 branes at a different fixed point, the spectrum is a bit different. If you put the D1 branes in the bulk, also the spectrum is different. So the Chan pattern, if for these D1 branes at the origin, is unitary. Because of the fact the Chan pattern is unitary, if you compute the central charge, you will get additional contribution compared to this general formula that you saw, that I presented you before. So this is not a minimal kind of string defect, if you want, because I have a Chan pattern already, which is not, which has already a U1 factor, if you want. So let me not go into details. You can also have string defects in the bulk, and the ones which are in the bulk are really of the minimum type, in the sense that if you take one of them, you have just nothing in the Chan pattern, SO1, which means nothing. And you have really the minimum number of degrees of freedom you can expect, you can imagine. And in this case, indeed, the left and right central charges are the ones given by this formula in the paper of Qumran, whereas in this D1 branes at the origin, you have additional contributions. More generally speaking, by the way, here it's one way to check this existence of these strings. These objects, these D1 branes in the bulk, have charges which are this in the geometrical basis, or this in the integral basis, if you want, and they satisfy, again, they are of this null charge type. What we did in our paper, here you see this anomaly polynomial for dimension, the 4 anomaly polynomial. What we did in our paper, we looked at all of this mini landscape of string defects in these supersymmetry cases. We checked in all cases, so this is again a pretty large set of defects. We always check that this, of course, first of all, it exists. Once we identify this, we don't need to check all the rest. What we checked is that this mini landscape are of 2 types again. Some of them are BPS, when we have this kind of self-dual kind of magnetic configuration on this kind of, we're talking about this kind of objects. So if you have self-dual kind of configurations, typically they satisfy all constraints of the Qumran wrote, except that there are additional contributions to the C left, C right, typically. There are always a bit additional contributions. Secondly, if you have actually we can write it, we can go directly to the conclusions. If you have non-BPS but stable, then generically the constraints are violated. This is not really surprising because they are non-BPS, but they are stable. So the stability does not guarantee these constraints. You really need them to be BPS, which is pretty natural from the point of view of the way these constraints were derived. So there is a whole world of non-BPS but stable string defects, which maybe have other kind of conditions, but we didn't really try to understand the conditions, consistent conditions for these ones. So conclusions for my part, again, we conjecture only consistent conditions from coupled to string defects, this kind of null charge strings, in case if there are at least one tensor. I forgot to say this, of course, makes sense only if you have at least one tensor. Models which have no tensor at all do not satisfy this, obviously. Central charges and most BPS string defects have additional left-right symmetric contributions, which could make us think that maybe the unitarity constraint maybe is too strong sometimes, maybe, in the sense that this was imposed by assuming the minimal kind of contribution to this C left, C right. So maybe it's too strong, but we don't have anything more to say for the time being. And just as the last comment, it would be interesting to find constraints, similar type, of course, for 4-dimensional supersymmetric series. but we don't have anything to say right now on this here. Thank you. And I think now I'll let Carlo to continue, unless if you have questions, specific questions for me.
So these extra contributions are what exactly? What is your understanding of them? I'm not completely clear about your...
For example, one example is this one here. So, for example, in this, if you have D1 branes at the origin, the churn pattern is not SO1, which means nothing, but it's U1. And because if here you have a U1, you have additional, for example, the second line would be the degrees of freedom of the center of mass of the string. This is the usual degrees of freedom of the string, but you see in the first line, just because, so in the first line, these are additional kind of degrees of freedom. And another kind of additional degrees of freedom which can arise is that if these string defects intersect, let's say D5 branes, for example, if they intersect D5 branes, you have additional master degrees of freedom which adds up to your C left, C right. That's
actually, there are extra contribution of other things to C left and C right, you mean?
Yes,
not the,
yes.
So there's no problem, actually. So.
No, except that the real C left, C right is typically bigger than this minimal formula, so maybe the unitarity constraint sometimes can be relaxed. Maybe, I don't know.
Right. So unitarity is just a constraint. It doesn't. It's not an equality, right?
Yes.
Oh, fine.
Okay. Yes.
Okay, maybe we can go for Carlos part of the...
Okay. Thank you.
So, okay, can you see it? Does it work?
Yes.
View, full screen. Okay, there we are. So before I start, I would also like to join Emilian in thanking Miguel and Irene for the kind invitation. And as Emilian anticipated, I will talk about the non-supersymmetric part. Okay, so we will have an analysis of some non-supersymmetric vacua of a specific type that we'll introduce in a second, and we see what the constraints on the existence of these defects, the one branes in these non-supersymmetric setups will tell us about. And so, of course, it's based on the same paper, on the same collaboration with Quentin and Cesar that Emilian mentioned before. So the main question that we asked, actually, which was the main motivation of our paper, is whether the consistency conditions of the one branes, which are coupled to the 6-dimensional tensor multiplets, as formulated originally by Kim, Xu, and Vafa, also hold when the supersymmetry is broken, or they have somehow to be modified, and some of them have to be relaxed or not. And the other question is if we can, the 6-dimensional anomaly polynomial and the consistency conditions discussed by Emilian, reviewed by Emilian in the previous talk, can tell us if supersymmetry is broken or has to be exact. So I will try to address these questions and try to find, by a top-down approach, to find models and examples which can answer to these two questions. Now, how to break supersymmetry in string theory? And I repeat also what Emilian said, we will do we'll be based mainly on perturbative string theory, where we have fully under control the CFT of the construction. And for what matters, we will concentrate entirely on type 1 constructions, orientable constructions with broken supersymmetry. So we can distinguish two cases, spontaneous breaking of supersymmetry, where we have some continuous deformations of the supersymmetric models. These are typically Sher-Schwartz or breaking by compactification. And in this setup, actually, we expect that all the constraints which have been discussed previously by Emilian also holds when supersymmetry is broken spontaneously. This is because the breaking is adiabatic, if you like, and can be restored if you go to some specific limit. And now the idea is that the constraints which have been reviewed by Emilian in the previous talk have not depend on the value of this adiabatic parameter, and as such should hold for any in any point of modular space when supersymmetry is broken or is restored. The other set of vacua which are non-supersymmetric are those where supersymmetry is broken at the string scale. These are typical from, occur typically in type 1 constructions. These vacua are now isolated, so they cannot be connected to supersymmetric ones by some adiabatic deformations, and thus are the ones with which I shall focus in the remaining part of the talk, and try to see what the constraints of buffer collaborators can tell us about this vacua. And these are precisely what models which go under the name of brane supersymmetry breaking, because as we shall see, supersymmetry, the breaking of supersymmetry is localized on the branes and not on the gravity sector. So let me just review very quickly what does it mean, brane supersymmetry breaking, and what is the signature of brane supersymmetry breaking. So typically when you do an orientifold, you have to introduce orientifold planes, which perform the projection, the omega projection on the closed string spectrum. And the supersymmetry, the brane supersymmetry breaking involves orientifold planes, which are not of the standard type, which orientifold planes which have a negative tension and a negative charge, but are orientifold planes of the type plus. So they can have orientifold 9 planes, for instance, in 10 dimensions, or combinations of orientifold planes, O9 and O5 planes in orbifold compactifications of the type plus minus, minus plus, which is essentially the same as the previous one, or both with of type plus. So this means that orientifold planes have positive tension and positive charge in this case, both of them, and in this other case, one has a negative tension and charge, the O9, and the O5, the positive tension and charges. Now, these combinations of the branes, of orientifold planes, sorry, are mutually BPS configurations, and as such, they preserve supersymmetry in the closing sector, which the closing sector is only sensible to the kind of orientifold planes which are introduced. So the closing sector in that case comprises typically a full gravitational multiplet, let's say in 6 dimensions with n equal 1,0 supersymmetry, and eventually a tensor, full tensor, and full neutral hypermultiplets, which come from closed strings which compactify the internal space. Now, Ramond-Ramond-Tadbol conditions, the difference with the supersymmetric setup, which was discussed by Emilian in the previous part of the talk, is that now the Ramond-Ramond-Tadbol cancellation condition implies that in order to cancel the positive charge of the O plus planes, one has to introduce anti-branes. And as such, by the anti-D branes and the orientifold planes which have been introduced previously are no longer mutually BPS, actually are not non-BPS combinations, and therefore supersymmetry is broken in the open string sector. Can be broken from all D branes or not just on a subsector of D branes, depending on the kind of model we are going to describe. So for instance, in these 4 cases that I listed before, in this case, we have to introduce a certain number of anti-D9 branes, 32 or 16 if you're counting physical D-branes that you can move from the planes. In this case, you have anti-D9 D5, or D9 anti-D5, or anti-D9 anti-D5 branes. And this is what is needed in order to cancel Ramond-Ramond-Tadbol condition. So in principle, there is no choice once you fix the orientifold planes whether you can or not break supersymmetry on the D-branes. And so these are the vacua that we are interested in. And in particular in this talk, and also on the paper, I will concentrate on 2 simple examples, which are 6-dimensional brane supersymmetry breaking vacua, which have been compactified on the orbifold limit of K3, which is the T4 mod Z2. And I will discuss 2 cases. One, the first one, which involves O9 plus and O5 plus orientifold planes, and thus it requires the introduction of anti-D9, anti-D5 branes. And the second case is the one which was introduced originally by Antoniadis, Dudas, and Sagnotti, which involves O9 minus and O5 plus planes, and hence has D9 and anti-D5 branes. Now, although in both cases supersymmetry is broken only in the open string sector and is broken explicitly, so there is no order parameter which can allow to recover supersymmetry in some corner or modular space, these two constructions I will show have quite different properties as for what concerns the consistency conditions reviewed by Emilian in the previous talk. So in particular, the model 1 shares all the features of the supersymmetric Bianchi-Sagnotti-Gimond-Polchinski models, which was discussed by Emilian before. There are some minor differences, and therefore one cannot say, let's say, all the constraints will be automatically satisfied. And from just an analysis of the anomaly polynomial and of the defects, it would be impossible to tell whether supersymmetry, the model, enjoys or not supersymmetry, whether supersymmetry is broken or not. Whereas in the other set of the other model, which is the one with O9 minus and O5 plus, there is no related supersymmetric vacuum which has exactly the same anomaly polynomial, so it does not share any property, any say feature of a would-be supersymmetric construction, and as we shall see, some Swampland conditions have to be relaxed in this setup when supersymmetry is broken. So let me start, let me go, well, already started, let me go through the models, and we start from model 1. So here I just review the spectrum of the construction. Here we have, as I said, O9 plus and O5 minus. And now since the number of tensor multiplets only depends on the relative signs of tensions and charges of these two objects, the O9 and O5 planes in this T4 mod Z2 construction. And in this case, the relative sign it's the same, is identical to the supersymmetric case. Now, it's not a surprise that the closed string spectrum has an n equal 1,0 supergravity multiplet in 6 dimensions, which is coupled to just one tensor multiplets and two anti-upper multiplets, as the BSGP model discussed by Emilian before. The open string sector, on the other hand, has to introduce, involves anti-D5 and anti-D9, 32 anti-D5 and 32 anti-D9, or 16 x 16, depending on the way you want to count them, in order to break to cancel the Ramond-Ramond tuples. And then the gauge group, what we find, the resulting gauge group is again of the U16 times U16 type, the one U16 localized on anti-D9 branes and the other U16 on anti-D5 branes. But now what happens is that the fermions can come in different representations with respect to the gauge group. So in this case, we have left-handed fermions, which are still in the adjoint representation. So if you like, we have a full vector multiplet in the adjoint representation of U16 times U16 gauge group. But now, if you remember what was flashed on the Emilian transparencies, we had a full hypermultiplet in the antisymmetric representations of the gauge group. In this case, only the fermions stays in the antisymmetric representation, so they come in the right-handed fermion in 120 plus 120 bar for both gauge groups. But the bosons, the four bosons, which before were super partners of the psi r in the hypermultiplet, now come in symmetric representations. So 136 plus 136 bar, comma 1, and vice versa. And also the same for the anti-D5 branes. And finally, we have another full hypermultiplet, which is in the 16-16 bar in the Bevel fundamental representation of the gauge group. So as you see, the fermionic part of the spectrum is identical to the supersymmetric case, but supersymmetry is now broken because there are on the open strings, because there are these scalars which are in completely different representations, and now fermions and scalars, these two objects, are not anymore paired by supersymmetry. Still, we can, and there are no tachyons, so the model is stable. And actually, I forgot to mention at the beginning, all the constructions that we are doing, we are going to review and we are considering in the paper, are stable non-supersymmetric vacua, in the sense that there are no tachyons which appear in the spectrum, although typically you have an uncancelled Navier-Schwarz tuples, and as such the background is not stable, and there is a back reaction of the configuration of O-planes and anti-D branes to the Minkowski space, and also the space, I mean, the real vacuum is definitely not Minkowski in this case. So we can move on. As I said before, the chiral spectrum is identical, so it's not a surprise that the anomaly
Sorry to interrupt you. What vacuum is, what corrections give you what kind of situation? Minkowski, de Sitter, or ADS in this case?
Well, there are some ADS depending. It depends. I mean, in the vacua, you can have vacua which are cosmological type, so they are dynamical, and then they have a natural compactification. I mean, let's say the analysis was done for the 10-dimensional model by Emilian and his collaborator Murat, which are of the type cosmological type, so time dependent, and they have a spontaneous compactification down to lower dimensions. Whereas if you look at static backgrounds, then the backgrounds are of the type anti-de Sitter. So in this case, the chiral spectrum, as I said, is identical. So it's not a surprise that the anomaly polynomials are the same as the ones discussed by Emilian in the previous part of the seminar. And so the anomaly polynomial has the standard trace R squared minus the contribution of the gauge fields of the anti-D9 and anti-D5 branes. This comes, so this is what I call the string basis, should have called the geometric basis, just to match the notation of Emilian. So this part here comes, sorry, the first part comes from the coupling with the self-dual tensor, which lives in the gravitational multiplet, whereas the second part is related to the anti-self-dual tensor, which is in the untwisted tensor multiplet, which is the only tensor multiplet that we have in this construction. As Emilian said, I mean, you can go through, so that's why I didn't flash any data here. So you can find the A and B vectors, the anomaly vectors, A and Bi, B9 bar and B5 bar. In this basis, they are not integer, but of course, the lattice is an integral lattice. But of course, you can then go to the integral basis, as Emilian showed, by just doing a rotation using a different, let's say, representation for the SO11 metric. And then in this case, the lattice is integral. And then you can go through the constraints, which are reviewed by Emilian in the previous talk. And then we can check whether you have a Keller form J, which satisfies all the constraints which have been worked out by collaborators. And indeed, in this case, you do find the Keller form, not surprising since all the data are shared with the supersymmetric case. And the analysis, I mean, so from that respect, everything is fine. You can then study which are the constraints, which comes from the defects, and also in this case we can have D1 branes, and actually also in this case we have studied different kind of branes, which are D1, let's say BPS D1 branes. I mean, mutually BPS with the anti-D branes, which have introduced. That's why here considered in this example anti-D1 branes. But you can have also non-BPS D1 branes, and eventually D5 prime branes, these defects which extend just in two directions in space-time and wrap the entire T4 mod Z2. So the analysis can be performed in a similar way. And for instance, in this case, for the D1 branes at the anti-D1 branes, sorry, at the orbifold fixed point, they carry the same kind of gauge group, which is a UR, and you have a spectrum which is identical to the supersymmetric one described by Emilian previously, aside from one difference, where now these scalars, which label the position of the D1 branes in the orbifold, in the T4 mod Z2 space, So these are scalars which are, let's say, vectors which have an index along the T-form of Z2. They are no longer in the symmetric representations, but because of the interaction with the O plus planes, they come in the antisymmetric representations. Still, you can compute the central charges. The central charges take this form, as Emilian was saying, with respect to the minimal case, which would be given just by this part of the formula. There is an addition of extra degrees of freedom, which are related to the interactions of the anti-D1 branes with the D5 branes, which sit at the same fixed point, or due to the fact that you have a unitary gauge group, which is supported on the anti-D1 branes. There is a shift C, which now, because of the fact that these states are in the antisymmetric instead of the symmetric representation, is lower than the supersymmetric counterpart. Still, also in this case, if you compute the vector charge, the charge vector, sorry, the Q, it satisfies in the condition that Q dot Q is equal to 0. So the conjecture, the null charge conjecture, the fact that there should be D branes which have a null charge in this sense, that the scalar product Q dot Q is equal to 0, is satisfied. And this follows from what Emilian was saying, in the sense that here we have only one tensor multiplet, and so this the self-dual part, which is in the gravity multiplet, and the anti-self-dual part, which is in the hyper-multiplet, they clearly descend from the C2 form that you had in 10 dimensions, so type 1 in 10 dimensions. And the D1 branes, these are not fractional, they are non-fractional, so they are charged only with respect to the untwisted tensor multiplets, and therefore they carry the same charge. These anti-D1 branes are the ones that you exist also in 10 dimensions, and therefore for them the charge satisfies this condition that Q dot Q is equal to 0. So again, you can move the D branes away from the fixed point. If you move the D branes away from the fixed points, of course, or you place them on a different fixed point with respect to the anti-D5 branes, then the data of the central charge, of course, the spectrum is modified. There will be different kind of degrees of freedom living on the anti-D1 branes, and therefore this shift in the central charges will be different and can be equal to 0 if the branes are moved in the bulk. So if you put again the anti-D1 branes in the bulk, as Emilian discussed, you really you get the minimal value of the central charge, as was discussed by Bafa and Shu and Kim. So I think that's it for the model 1. And now we can move, unless you have questions, we can move to the model 2. So let me summarize. For model 1, the analysis is identical to the one performed in the supersymmetric case. So you can find the J, you can find the Keller form, which is satisfies all the conditions. Then you can you find that the Kac-Moody levels, I didn't report here, but the Kac-Moody levels are all positive for the various for the gauge group which is on the D1 branes, and the unitarity constraints are all satisfied. Now let me move on the second case, where instead we will find some surprises. So in this case, the closing superstring now involves O9 minus planes, which are the standard one, but together with O5 plus planes, which have positive charge and positive tensions. And now, as I said before, since the number of tensor multiplets depends on the relative signs of these two objects, the twisted sector, the omega projection is reverted on the twisted sector of the theory, and therefore all the fixed points, they don't contribute with hypermultiplets, but contribute each of them with tensor multiplets. So since we have 16 fixed points, the theory comprises 17 tensor multiplets and only 4 hypermultiplets from the untwisted sector. Of course, we have n equal 1,0 supergravity coming from also from the closed strings. Now, this model is quite peculiar because it does not admit a supersymmetric spectrum version with the same fermionic spectrum that I'm going to discuss right now. So there are no choices, let's say, of whether you can preserve or not supersymmetry. In this case, the open strings involve, actually here there is a mistake, they involve D9 branes, sorry, not anti-D9, because you have to cancel the standard, the negative Ramond-Ramond charge of the O9 planes, and anti-D5 branes. Now, because of this D9 and D5 branes, the presence of D9 and D5 branes, together with the O9 minus and O5 plus, the gauge group now is not anymore unitary, but it splits into the product of some orthogonal gauge groups, which live on the D9 branes, and some symplectic gauge group, USP16 times USP16, which live on the anti-D5 brane. So these are the vector bosons, which are in the adjoint of this gauge group. But now for the fermions, you see already the breaking of supersymmetry, because the fermions, they would be gauginos, which would be superpartners of the vectors. Now they all come in the antisymmetric representations. Now the antisymmetric representation is the adjoint for the orthogonal gauge groups. So this, you can reconstruct a full vector multiplex on the D9. After all, D9 branes and O9 planes are mutually BPS, so you expect that the spectrum on the D9 is confined on the D9 is supersymmetric, but on the anti-D5, the fermions come again in the antisymmetric representations, which is not the adjoint of unitary gauge group. So again, in this case, the supersymmetry is explicitly broken in the open string sector. Then you can have a full hypermultiplet, so for scalars and right-handed fermions in the 16,16, so in bifundamentals of the orthogonal gauge group and bifundamentals of the USP16 gauge group. So this part of the spectrum is still supersymmetric, but then there is a signature of this model, in the sense that we have, let's say, half fermions, so symplectic Majorana-Weil fermions, which are in the this bifundamental representation, so in the 16,16, so 16, one fundamental of an SO gauge group and one fundamental of the USP16 gauge group, and similarly for the other pair. Now, of course, having half a fermion in theory, in principle, is inconsistent, but this model actually, the fact that this fermion, these symplectic Majorana-Weil fermions, are in a representation, carrier representation of a symplectic gauge group, then you can prove that the construction is consistent, and even if you have this half fermion, the model is fully consistent. And finally, you have two scalars, which are in this representation, which are completely different. So also this sector breaks supersymmetry. Now, as I said, this model does not admit a supersymmetric version, which has exactly the same fermionic spectrum of the theory. And this is mainly due to the fact that in the supersymmetric version, you should flip the representation of the bosons in this part of on the anti-D5 brane. So which means that you should if this model exists, it would have a gauge group which is SO16 cross OC16 also on the anti-D5 branes. And in this case, this half a fermion, which is in this bifundamental representation, would yield inconsistencies in the construction in the model. So this is one of the reasons why there is no supersymmetric version of the construction which has perturbative, at least, which has the full which has 17 tensor multiplets and a full supersymmetric open string spectrum. So this is about the setup of the construction, and then we can go on with the studying of the anomaly polynomials. And here maybe is what Emilian was saying, that in this, the difference between the geometric basis of the string basis and the integral basis. So here we have 4 gauge groups, the 2 symplectic for the anti-D5 branes and the 2 orthogonal for the D9, and the label F1 and F2 label the 2 orthogonal gauge group which live on the D9, and G1 and G2 the 2 symplectic gauge group which live on the anti-D5 branes. And this expression clearly tells us, you can read immediately. I mean, this would, I don't want to enter too much into details because it would take me too long. But this descends from the tadpole conditions and from the geometry and of orientable planes and D-branes, how the D-branes are the couple to the Ramond-Ramond forms in the various tensor multiplets, and also how the D-branes are distributed among the fixed points. So for instance, in this case, you see that you have the orthogonal gauge groups, they enter with a plus sign with respect to the symplectic one, those which live on the anti-Defect branes have a minus sign, and this reflects the fact that the D9 branes and the anti-Defect branes have opposite Ramond-Ramond charges. So when they couple with opposite sign, with opposite charge to the self-dual form, which leads to the form in the gravity multiplet, the 6 forms in the gravity multiplet. These other terms instead, they have the same charges, and then this is the coupling to the untwisted tensor multiplets, and the untwisted tensor multiplet also is responsible for the trace, accounts for the trace R squared. And in the second line, instead, you can read the 16 contribution 1 plus 15, which come from the twisted tensor multiplets. And this really shows which is how the D-branes are displaced. And indeed, the D9 branes, which are the F1 and F2, they invade the full T form of the two compact space, and therefore they probe each tensor multiplets which lives on different fixed points. So that's why the F1 is distributed both in this term and in the other 15 copies of these other which correspond to the other 15 tensor multiplets. But now the D5 branes only sit at the single fixed point, and thus they couple only to one specific twisted tensor multiplets, and that's why they only appear in this term here and not in the other terms. So this is the geometric basis which is preferred, let's say, by string theory, but again, also in this case, if you compute the vector, the anomaly vectors, the A and the BIs, these vectors are not integral. The lattice, the anomaly lattice is always integral, so the product of A dot A dot B, and B dot B is integral, but the vectors themselves are not. Of course, you can rotate, you can use an S1NT rotation and go to the integral basis, where now the anomaly polynomial takes this form. So the coefficients are all, the A and B's have integer entries, but the anomaly polynomial has nothing to do with the geometry of the branes and the orientable planes that you are involved in the setup. So, let me move. So the anomaly lattice, as I said, is always integral. Of course, this product are also 117 invariant, so they take always the same value for the two anomaly polynomials. But now the integral basis, which refers to the second choice, are given here. So this is a solution of this constraint, these products, these constraints, which has only integral entries. Now, in this case, you can again check whether the Keller form exists in this non-supersymmetric setup, and what you find is that the condition J dot J positive, J dot A negative, and J dot B I for each I 1 to 4 related to the 4 gauge groups positive is not anymore, cannot be imposed. In fact, this condition with these choices of A and B, which are given here for the integral basis, lead to these 4 conditions for the entries of the Keller form, And clearly they are incompatible among each others, and there are therefore there are no solutions for the J form. Now, this is, in principle, is not a problem because the construction is not supersymmetric, so it's not obvious that you have to find all the constraints, the existence of the Keller form, which is typically related to supersymmetric Lagrangians and considerations, but this differs, for instance, from the previous case, where although the model was not supersymmetric, we were still able to find the J. So depending on the construction, on the setup, you have to eventually relax some of the conditions, which seems to be really tied to supersymmetry and not to the physical requirement for when supersymmetry is broken, as in this case of brane supersymmetry breaking with O9 minus and O5 plus. Now we can move to the defects, to studying the defects on the setup, and in this case we can study the D1 branes. So the D1 branes are the defects which are mutually BPS with the D9 branes, which are part of the ground. And these D1 branes now in the VSB model now have a gauge group, supported gauge group, which is orthogonal, so it's an SOR gauge group, and the spectrum is given in the table here. Clearly, okay, this is the anomaly inflow, and so this is the anomaly polynomial, sorry, which which is associated to the spectrum, which lives on the anti-D1 brane, on the D1 branes, and this anomaly polynomial is cancelled by the inflow only if the charges take this form. And here I've given two solutions. So these are the two charges, and these charges are given in the geometric basis, if I remember correctly. And in this, so these charges, there are two, actually there are 16 different solutions, where the -1 here, so the coupling to the self-dual tensor multiplets tensor in the gravitational multiplet, and the coupling to the untwisted tensor multiplets are fixed in all solutions, but then you can just move the -1 in the 16 positions, and this reflects where you put the -1 in the various configurations reflects the fixed point which on which the D1 brane is localized. So, for instance, in Model 1, the D1 brane is localized on the let's say the first fixed point, where also the anti-D5 branes are localized, and therefore the spectrum you have these extra states on the Born volume of D1 branes, which are open strings which stretch between the D1 and the anti-D5 branes, and these are massless. Whereas in the second case,
Carlo, sorry to interrupt. We are reaching the end of the allotted time of the seminar, so maybe it would be.
Yeah, I'm going.
We will only be able to have a short discussion now.
Yeah, sure. Let me just 5 minutes, and then I will. What is it? Okay. I went also over time, and I apologize. So this is goes to anti-D1 branes, which sit at different fixed points, and so the D1 anti-D5 strings are massive. So these extra degrees of freedom are not there. Now, what happened is that in these cases, we can compute the Kac-Moody levels, and the Kac-Moody levels in the two solutions take this form, and you can see that here there is a Kac-Moody level which is negative. This entry is negative. Q dot B is negative. Q dot B4 is negative, and this is due to the fact that if we go to the previous slide, then the spinors, which are charged with respect to the second symplectic gauge group on the anti-D9 branes, have an opposite chirality. So this means that the model is not inconsistent, because remember from the KSV conditions, the K should all be positive, and of course this is the case if supersymmetry is preserved on the defects. But when you break supersymmetry, then you can have both positive and negative Kac-Moody levels, and this simply implies that you are realizing the Kac-Moody algebra. Not, I'm sorry, I enlarged the slides. Not only on the left mover sectors, but sometimes in the left movers and sometimes in the right mover sectors, and this is consistent with the fact that supersymmetry is broken. And also here, okay, you can add these extra terms, 16 and 16, to the left and right central charges, which are due to the interactions, in this case, of the D1 branes with the anti-D5. If you move in the bulk, you can also move the D1 branes in the bulk, and in this case, of course, moving them in the bulk, there is no interaction with the anti-D5, so the Kac-Moody are simply of this time, which are positive. The central charges takes the minimal value, and with the Q dot Q is equal to 0, the null charge condition is satisfied. And I think I can just jump to the conclusion, and then I have an answer maybe to your question about the Q dot A and Q dot Q. And so now when you break supersymmetry, of course, some of the conditions have to be relaxed, and this is not a surprise. And for instance, the existence of the carrier form is not always guaranteed when you break supersymmetry. I've seen 2 examples where it does exist and where it does not, and it would be interesting to understand which are the implications for the low energy actions and the couplings in the 2 descriptions, in the 2 models. Kac-Moody can be realized in both left-moving and right-moving waves on the D1 branes, but from our analysis, and the null charge defects always sticks, also when supersymmetry is broken. And thank you very much, and sorry for being over time.
Okay,